Next, I'm going to solve example number 17. It's on page 178. It's about drag force. It's like kind of using the equation for the first time. So I want to go over the equation first. Drag force is given by this relation here. It is 1/2 rho v square ca. So let's just kind of see what those values are. So D is the drag force, rho is the density of the fluid. And since it's the density, it's mass over volume. In some of the problems, they're not going to give you what it is. They're going to tell you if it's air or water or whatever it is. So you may need to look at the table 14.1 on Wiley and look for the density values, as we will do it on the problem coming up. V is the speed, and that is really the relative speed between the fluid and the object. So it could be the object moving relative to fluid, or fluid moving relative to object, or they're both moving, but the relative speed, whatever it is, that's what we use in the equation. And C is the drag coefficient. It's again an experimental value and can change from 0.1 to 1.5 typically, and the lower the better for aerodynamic purposes. And A is the area, but it's we gotta be careful with this one. It is a 2D area. That means like if you shine a light over a sphere, then you would see the shadow as a circle. So it's not the spheres. If your object is a sphere, it's not the area of a sphere, but it is the circle area. So it's not 4 pi r square, as you can see here. It is pi r square as the area of a circle. Again, if it's you have a cylindrical object, if you look, depending on where you are shining the light, kind of the shadow area, so it could be a rectangle or it could be a circle, right? So you're gonna kind of think about that and find out the frontal or the shadow area. Okay, so those are the things that we're going to be looking into in this example. And so the example states that there is a 5 centimeter diameter ball. So I'm gonna just start changing things as well, because centimeters is not an SI unit. It's in SI units I need to make it a meter. I'm dividing by 100, right? And it is a diameter as well, so I'll probably need the radius instead of diameter, and radius is half of a diameter, right? Let's just keep that in mind. So it is dropped off a building. And what is the drag force on the ball when it is velocity is 30 meters per second, and if the ball's drag coefficient is known to be 0.5, so they're giving us the C and the V. If the ball weighs 4 newtons, they're also giving us the weight force. Compare the drag force to the object's weight. Okay, so let's just think about the free body diagram first. Since the velocity is shown on the figure, I don't want to put the forces there because I don't want to think that V is one of the forces. So there is the weight force, and there is that drag force. Object is going down, right? So I can think about this as y-axis is downward. Okay, so let's just find out the drag force on the ball. So what assumptions do we make? We do not ignore air resistance, right? Because we have drag. And important thing is, again, that drag coefficient. We're going to say that drag coefficient is constant. You can also talk about one-dimensional forces and motion. It's a particle, those kind of default things that we've been discussing, right? But again, since I'm just highlighting the one that is kind of new to this problem. What plan do we have? We have an equation. We're just going to plug things in. So use drag force equation. And what estimation can we make? So it says that the ball weighs 4 newtons. So we have another force to compare with. So what happens is initially when you leave the ball, when you release the ball, at that moment V is still 0, right? Initially the object is at rest. So when V is 0, drag force has V in it. So initially there's no drag force. Drag force is something that builds up with the speed. As speed increases, drag increases. But it is V squared, so it's like if V is increasing, drag is even increasing more because we have to square the velocity. So we're going to think about that at the end, but what I want you to see is t is equal to 0. When I release the ball, there's no drag force, there's just weight force. And it builds up at 30 meters per second. We will find out what the value is, but I don't expect to be more than the weight force. Later on, we are going to talk about the terminal velocity, and we're going to see that that happens when the weight force is equal to drag force. So they're going to be equal to each other. But this problem, there's no extra wind or something, so it's just a drag force. And I expect drag force to be less than the weight force, which is 4 newtons. Okay, so for this solution, let's first write down our equation. 1/2 rho v squared CA. Right. Okay, so let's put the numbers in now. Let's just kind of think about what we have. Actually, before putting the numbers in, let's just think about what A is. I'm just gonna write it here. It's a sphere, but again, I'm not gonna use the area area of a sphere because this area is frontal area or the shadow area. It is in 2D. So 2D of a sphere is a circle. So it is going to be in the form of pi r squared. Since r is half of d, you can write this as pi d over 4 and d squared because you need to square d over 2, right? Now, knowing this, let's plug the things in. 1/2 rho is the density. So density of air is in that table 14.1 is given as 1.21. Density is mass over volume, so it's kilogram per meters cube, and that is rho. And velocity is given as 30 meters per second in SI units, so we don't need to convert it, but we need to square it. And C is given as 0.5, and we said that we're keeping this constant for this problem. And area is pi over 4 and d squared, and d is 0.05 meters. I'm gonna square that. Okay, so that's all we have. Let's see what we got. The number wise, we get, let's see, 0.53. Let's check the units. So we have kilograms. I'm gonna just write what I have. On the top, there's meters cube at the bottom. There is meters square because the velocity was square. Meter square on the top, second square on the bottom, and another meter square on the top. So that would give you unit wise 0.53. Let's just do quick cancellation. So meter square will go away with 3. I have left with meters. One of those meters will go away with this meter square. One of the meters. So we have kilogram meters per second square, and we know that that is newtons, right? So that's my drag force. And as you can see, this is much less than the weight force, right, which was 4 newtons. So the question is, what happens if V is doubled? The speed goes up by 2. What happens to the drag force? if you look at the equation, V is squared. So D is proportional to V squared. If V is doubled, you're squaring that. So D is going to go up by 4. Okay, so it's going to increase by 4. Okay, again, I encourage you to read the discussion part, but this is how we are going to deal with the drag force equation.